Hello everyone, I'm Ishara Dharmasena. Uh, Currently, I work as a Doctoral Prize Fellow at Loughborough University. My research area is related to wearable electronics, textiles, and energy harvesting research areas. Um, and Today I was invited by the SCF, Asil, and the crew to give you some introduction into my research areas, research activities, and a little bit of my experience on the PhD project that I have conducted and what I have gained through those experiences. Today I have a presentation with regards to my research activities and how things have developed, including a brief introduction into the technological landscape. And then we will look into different applications of this technology, how it can help us to lead a better life in terms of making our lives more easier. So let's move on to the presentation. It's the title is Towards a Smarter World, Energy Harvesting for Wearable Electronics. As I have mentioned, my name is Ishara Dharmasena and I work in Loughborough University. I have given my email address in this slide, so if in any case you need any questions or if you need to connect to get information regarding something, you can contact me at any time. Within today's presentation, we will discuss about the evolving technologies in today's environment. And then we will talk a bit about smart textiles, what they are, what wearable electronics are, and what sort of applications are they used for. Then we will discuss briefly about some of the challenges in smart textiles and wearable electronics, and how we can overcome these challenges, and mainly how power generation of these devices are performed at the moment, and what sort of improvements that we can expect in these things. Then we will talk a bit about upcoming energy technologies and some of our recent research activities related to these. Smart textiles or wearable electronics are electronic related components that we basically can wear. So these can come in form of flexible and stretchable devices which can fit into our bodies, or they can be devices that we can wear like watches, and also they can be integrated into the textile so that we can wear it in a shirt or a pant or something like that. Basically, if you consider smart textiles or wearable electronic devices, they have different components within these devices. So they might have sense elements, so they can sense our environment, different stimulus in our environment. For example, these devices can measure temperature, heart rate, or other health related activities, or it can be some sort of a chemical related stimulus, for example some toxic gas or something like that. So there's a sense element which allows these electronic devices to sense our environment. And then there can be actuate elements. So once you actuate elements, processing elements, and conductor parts involved in this electronic device, once a sensor picks up some sense, it will be sent to the processing unit, which tries to process this data and either to identify what kind of a sensation it is, and then what sort of actions do we need to take, does the system need to take in response to this stimulus. And then this information will be sent to an actuator unit, which will be used to communicate this data or do some action in response to this sense. So for all these processes to happen, electronic signals or electronic currents need to be conducted from one location to the other one. So this is done by these conduct elements which connects these different components within the system. There are many examples for smart textiles and wearable electronic devices. They are used for many different purposes, to sense health information, to get information about some sort of environmental conditions and so on. We will look further into details about these activities in the future slides. Talking about today's technological environment, our world is changing very rapidly. If we talk about the recent past and the current situation of these technologies, you may have heard about a term called Internet of Things, or 5G technology, or WSN, which means wireless sensor networks. If you think of Internet of Things, for those who are not very familiar with this technology, what this basically does is it makes the things around us to be much smarter than they are at the moment. For example, this involves integrating electronic sensors in our clothing, in our vehicles, buildings, maybe on trees and so on our roads. So by doing that, this creates a smart environment so that the objects around us can gather the data on our surrounding, and they can interconnect with each other to communicate that data to make our lives easier. For example, this might include integrating some sort of a sensor in our clothing so that it can detect our vital signs, for example, heart rate or blood pressure or something. And even with us knowing, these systems can communicate it to our doctor and then alert him about a certain situation. Or if we consider another example, think if our cars are embedded with these kind of smart sensors, they will be able to detect faults in our cars, and then probably in one hand it will alert us about these activities, and then on the other hand it can communicate with let's say the nearest garage and then allocate us a time slot for us to go and then get it repaired at that moment. And in the same time, it can report the fault to the manufacturing company, the car maker, and then make them aware about this situation, and then probably help them to develop better products in the future. Likewise, the target of this technology is basically to communicate within the devices in our environment to make our lives easier. If you talk about the 5G technology, it's the next generation of 4G, which provides us with very, very fast internet connections to communicate data better. And similarly, wireless sensor networks allow better communication of data to make our lives easier. So today's technological environment is rapidly changing and rapidly evolving. So similarly, the devices which are incorporated with these technologies will be much smarter and much faster. If we think about IoT predictions by the end of 2020, this estimation was done maybe around 3 or 4 years before now. So at that time, it was estimated around 10 billion of devices will be available to the people in the world. But by the end of 2020, this number will go up to around 50 billion devices, smart sensors and smart devices. So if we consider this as an average, it will be somewhere around 6 to 8 devices per person around the world. So this is a huge number of devices and a huge development in terms of the day-to-day lives of people. These applications can be used in different activities, as I have mentioned before, in the automotive industry, healthcare sector, consumer electronics, utilities, and so on. If we consider the market value of many of these devices, it presents us with huge market opportunities, huge economic opportunities. For example, this is an estimation from 2014 where people have gathered information about different market segments of smart textiles. In the first image, I have given some information about the market share and also growth rates of different smart textiles products in various continents. As you can see, the America has a large share of the market in this area, and if you think of the growth rates, Asia Pacific dominates it with a 44% of growth rate, and by now this data might have been significantly changed, with Asia becoming more and more of a leading member in this market. And if you consider the market segments or different application areas of this technology within the North America, you can see how these are distributed in terms of the protective and military equipment, architectural developments, transportation, fashion and entertainment, personal electronics, etc. So if we think about it in a Sri Lankan context, we already have a well-developed textile industry, but currently there's a huge challenge for the Sri Lankan industry from countries like Bangladesh, China, and so on, in terms of labor costs and low cost products. So in order for us to develop and sustain in this market, it's very important that we concentrate on value-added products, like different modifications or new technological products, which smart textiles area will provide to Sri Lanka. And also it gives you an opportunity to diversify your products, and to reach a niche market where there are a less number of competitors to develop these kind of products. So thinking about smart textiles, wearable electronics, and doing research and developments in this area is actually vital for us to develop as a country. This is a futuristic demonstration of what our future might look like in a few years. If we consider a typical cafeteria in the future, we might have clothing and wearable devices integrated into people itself in different ways. For example, there might be flexible and mobile glucose sensors, and ECG and other health monitoring parts can be integrated into your clothing. There can be smart glucose sensors connected to your skin, on-skin electronic devices. EEGs and other health sensors can be integrated into your hats and other things. And also there can be light and chemical monitoring sensors integrated in terms of lenses and all. So in near future, there will be a large number of electronic devices either connected to our bodies or combined with our clothing. Here are some of the recent developments in smart textiles and wearable technology areas. Again, as we discussed in the previous slides, they can be things that we wear. For example, things that are connected to our pants or t-shirts or shoes, or things that we wear. For example, goggles, wristbands, watches, headphones, and so on. So in terms of health monitoring applications, many of these devices are capable of monitoring heart rate, blood oxygen levels, our breathing rates, and other vital signs, maybe also cognitive functions and sleep patterns, and so on. So developing better technologies than the devices that we have today is critically important to make them more wearable and more comfortable in their applications. So as we have discussed in here, many of these applications can be either connected to textiles or they can be connected to our body parts. For example, they can be on our skin as epidermal devices, or they can be placed inside our bodies, connected to different organs or muscles for health monitoring and regulation purposes. This is one example of how people have developed different textile related applications. So in the earlier days, what people used to do is to attach the electrical component into a textile by sewing it or binding it or some other technology which in which the textile only acts as a substrate or an external element. So but with these new developments, the connection between the textiles and electronics devices are becoming more and more integrated. For example, in most recent developments, what scientists are trying to do is to produce a textile which has an active function in contributing to the smart electronic applications. In this example, there's a related developments that they have given for energy storage and energy harvesting purposes, where a textile is modified from the fiber stage by using different chemicals to develop an energy storage device. The second category that I have talked about, which is related to integrating the electronic devices with our body itself, electronic skin is a prime example. In here, what scientists are trying to do is to imitate the functions of the skin using electronic devices. So for these, what they normally do is they use flexible and stretchable polymers. For example, something like polyurethane or something like PDMS, which is a silicone type. So they use those kind of polymers as flexible and stretchable substrates, which are somewhat similar to skin, and they try to functionalize these polymers or modify these polymers by giving different electronic functionalities, by adding different materials and metals and so on. So these devices, these skin-like patches, if I say, have properties such as flexibility, good resolution. They can be created as large devices, and they can sense parameters such as force and tension, and in certain cases some chemical stimulations and so on. So these kind of things will be very useful especially in applications like robotics, where you can have these artificial skins connected to robots, and they will in future be able to sense like the humans doing. And probably, hopefully, in near future, people will be able to use these electronic skins to replace our normal skin. For example, if there's a patient who has severe burns or something like that, we might be able to replace their damaged skin using these electronic skin components. That's a very futuristic idea, and people are still working towards those applications. But at this stage, mainly scientists are focusing on developing basic functions like force sensing, force differentiation. For example, if there's a tensile force or pulling force or pressing force, a compressive force, how you can differentiate between those different force types. So that's something that the scientists are working at the moment, so that the person who's using the skin will be able to identify what sort of touch is being given into this skin patch. I have included a small demonstration about how these electronic skins work and how they are being currently developed from a different research group, Somya research group of Tokyo University. So as I have mentioned, these devices can be very lightweight, flexible, stretchable. You can even crush these devices in certain circumstances and they would still remain their mechanical properties. And these are the polymer types that they use as the flexible and stretchable substrates or surfaces to produce electronics on the top of these. So this is a tactile sensor which the skin can sense when you are moving your fingers on the skin. And this is a flexible and stretchable display that they have produced using a e-skin type of a device. Okay, so that's a nice demonstration on how these technologies can benefit people in terms of health monitoring and other applications. So now we will look at some of the challenges that we have currently and how people are working to overcome these challenges. As you have seen from the previous device applications, these devices are very stretchable, flexible, and skin-like structures. And also, even when you connect electronics into textiles, they can't afford to be too bulky. They can't afford to be too rigid, or otherwise when you wear those, it will be very uncomfortable. So one of the key challenges in these technologies is the powering of these sensors and electronics. Conventionally, as you all know, we use small batteries and capacitors and other related electronic equipment to power these. In earlier days, we used to have wires hanging all over our smart devices so that it can be powered, and currently we are using portable batteries or capacitors which can be charged from different areas. So what it does is it adds a bit of bulk and relatively higher weight and rigidity into the textile structures or electronic structures. And in addition, time to time, you have to take these batteries out, charge it, and put it in order to operate continuously. For the moment, it is sort of manageable, but in future, this may not be manageable for much longer. For example, imagine if you had to have a particular sensor integrated in your body, an implanted device kind of a thing, and what if you had to cut open your body once in every 10 years or something to replace the battery? That wouldn't be ideal, right? So similarly, especially if we think of the IoT technology that I have told you before, there will be thousands or maybe millions of sensors in our surrounding, maybe within our house itself. So if you needed to change the batteries or something, in each of those cases, you'll have to do a lot of work to do that. That's a very simple example. So likewise, in order for us to make these electronics better, we need to be able to find ways to make them work by themselves, to make them sustainable and self-powered. So what I mean from that is these devices should be able to capture energy from our surrounding and then convert it into usable electrical currents. And then they should be able to maintain this capability and then maintain themselves without needing to replace or recharge. That would be the ideal situation where these electronics will be very, very useful for us. This shows some of the implanted electronic devices and also on-skin electronic devices. As I have told you before, in these kind of applications, it might be very inconvenient if we had to recharge or replace batteries time to time. So therefore, constructing self-powered systems is a very highly desired area in the science and technology arena at the moment. There are different methods that we might use for energy harvesting purposes. So energy harvesting, basically what it does is it captures different energy sources in our environment. For example, mechanical energy. So when people are moving or walking around, there's a lot of motion produced. This motion can be used as an energy source. Solar energy, we have free energy from sunlight coming throughout the year. And this energy is quite sizable. And also thermal energy from our body, from the outside environment. There's a lot of heat generated, and there's chemical energy in our sweat and in other forms. So energy harvesting focuses on capturing this energy from different technologies and converting this into electricity, so that these electrical currents can be used to power different devices. And also, these energy harvesting technologies are estimated to have a very high market value. For example, by the end of 2020, it's predicted that these energy harvesting devices would have a market value of around 2.6 billion pounds, which is quite a large value. So there's a lot of interest currently in this area. And now the challenge is to capture as much energy as possible from our surrounding and convert it into electricity in the most efficient manner, so that we can make use of the maximum amount of energy available in the environment. This is quite challenging and tricky, especially when it comes to wearable and flexible devices. Among these different technologies, I will talk about two different technologies that are commonly used and that we are involved in developing. First one is solar cells. So there can be many different solar cells available to us. So there are silicon-based solar cells, OPV devices, or optical photovoltaic devices, based mainly on polymers, and there are perovskite solar cells, and there are different types of solar cells that people use for different applications. So there are different generations of solar cells which are being developed currently, and this demonstration is from one of my colleagues' publications, Dr. Imaka Jayawardhan, who's in University of Surrey. So that group and also some of the groups in Loughborough University are developing different solar cells which can be integrated into textiles and which can be used as flexible and stretchable devices to harvest energy. In terms of mechanical energy, my work is mainly related to mechanical energy harvesting. So as I have mentioned before, mechanical energy is the energy which is generated in the form of motion in different day-to-day activities. If we for a moment think about the energy requirements of most of the portable and mobile electronic devices that we use today, with the new electronics, their power consumption is quite efficient. For example, most of the health sensors that we use can maybe using a power of around 10 to 100 microwatts. That's a very small amount of energy. And even the medium range applications such as activity bands or smartwatches might be using several milliwatts of power. And even the large devices that we use, for example tablets and smartphones, may be using somewhere in the range of few watts of power. So these power requirements are not very large, and they are becoming more and more manageable with the electronics developments. Now, the important thing is we should be able to construct efficient methods to capture energy and fulfill these power requirements using energy harvesting devices. Now, do we have enough energy to capture in the environment? That would be an interesting question. Um, if we think of a person who is moving or who's working at as a normal speed, uh, in this slide you can see the power produced in different parts of the body. Um, you can see in shoulders it may be in the range of several 2.2 watts, and in hips it's around 38 watts or 40 watts or something like that, and in knee and ankle it can go above 30 watts. So this is the amount of harvestable power in different parts of our body when a person is walking at around 4 kilometers per hour speed. Now, in order to capture this energy and convert into electricity, the technology I'm working on is called Triboelectric Nanogenerators or TENG devices. So TENGs work in a very interesting concept. So we all know static electricity. We have experienced static electricity during lightning or touching a Van de Graaff generator, or if you take a balloon, rub it in your hair and put it on your wall, it will stick, right? Or it will attract small pieces of paper. That's because of static electricity. When two different materials are contacted or rubbed against each other, charges from one surface jumps onto the other surface. So one surface will be positively charged and the other surface will be negatively charged. And how this charging happens depends on the position of this material in the list called the triboelectric series. If you take a material on the top of this series, it will be positively charged, and if you take the materials on the bottom of this series, it will be negatively charged. So this is a brief introduction into triboelectric technology from one of the leading researchers in this research area, and you can now see parts of this video. So these triboelectric devices can be very small devices made out of flexible polymers.
Energy technology, I believe they're going to change the world we live in the near future. We look for new energy, but energy is around us everywhere, all the time. But most time we waste them. Until recently, we find this can be a very important effect for energy. Now, how does it work? So what you see here is A materials and B material. When they become physically contact, there's a charge transfer. If they are separated by a gap, there's a voltage generated. The second mode is sliding. If you have two materials, they slide one against the other one. You can also have a charge here. One mode is physical contact, and the other one is sliding. These are the two basic modes we use for electricity generation. This is called trouble electrification, or scientific called contact electrification. And this occurs for almost any materials we know today. Why do we use nanomaterials here? By using nanostructure on the surfaces, we can largely increase the surface area and hugely enhance the charge transfer. Without use the pattern, the power density is different by 1,000 times. When we first invented this was fall of 2011, the output was just 3 volts. Today, our best can be 10,000 volts. Mechanical energy is everywhere, independent of weather, independent of day or night, independent of season. So anything you can think of, smaller scale, from finger tapping, from your touchpad, from the walking to car motion, even train motions, we can do that. We harvest energy we have been wasted for years. We never use them. So I anticipate this can not only contribute the power source for portable electronics, but also can contribute power source for large scope of energy need. It can contribute significantly to the worldwide energy need in the near future. And we even think for big ocean wave, theoretically, let's say 31 terawatt energy can be harvested. That's twice of today's world energy consumption. It will not take too long, 5 years.
Okay, so that's a brief introduction into the earlier developments related to triboelectric technology. Now, let's look into the details of this technology a bit more and see how these devices actually work. Now, so this is okay. So in here you can see that there are two different materials shown in two different colors. Let's assume this is the first material and this is the second material. So when these two materials are contacted with each other, they get oppositely charged. One material will be negatively charged and the other material will be positively charged. Now, when these are charged in the initial scenario, both positive and negative materials will be almost on the same plane, right? So in this situation, there will be no output from this device. However, when these two layers are separated by a particular distance, the negatively charged layer is closer to the electrode or the conductive layer on the back side of it, and the positively charged layer is closer to the other electrode. So the structure of the triboelectric generator is constructed in a way that you have two non-conductive materials, and on the back side of those you have two conducting materials. For example, let's imagine you get two plastic sheets and you put metals on the back side of both these sheets. Now, when these are separated by a small distance, the first metal layer is closer to the negatively charged layer and the second metal layer is closer to the positively charged layer. The triboelectric charges on the surface don't change for longer distances. Because of that, it induces a negative potential. It gives a negative force on the electrode, and on the bottom electrode it gives a positive force or positive induction. Because of this positive nature and the negative nature of the charge layers, it creates an imbalance between the potential of the two electrodes. Therefore, it drives a current from the bottom electrode to the top electrode to balance this potential difference. So when the layers are separating, there will be a charge flow or current flow from the bottom electrode to the top electrode. Now, when you contact these layers again after their separation, these triboelectric charges are coming back to the same plane. Because of that, the charge flow which happened previously to cancel the potential difference will reverse, and there will be a charge flow or current flow from the top electrode to the bottom electrode. So this device basically acts as an alternating current generator. When you're separating triboelectric layers, there will be a current in a particular direction, and when we are contacting these layers again, the direction of the current reverses and there will be a current flow in the opposite direction. So when you use this device, these layers are contacting and separating continuously, giving you an alternating current output. During the first part of our studies, what we have done is we have done a lot of theoretical work and simulation works to correctly understand how these devices are working and how we can make best devices out of the resources that we have. Here are some of the developments related to triboelectrics in our research work. In our activities, what we have done is we have concentrated a lot on textile-based triboelectric devices, energy generators. In doing so, we have used different material types. For example, nanomaterials such as nanofibers and nanoparticles were used to develop different textile materials which have the triboelectric properties. In here, we have used conventional textiles, for example, cotton, polyester, silk, and so on, and then use these nanomaterials on the top of those textiles to make very active triboelectric layers, and from that we were able to produce highly performing textile based triboelectric devices. For example, if you consider a 5 cm by 5 cm very small device that we have produced, it can produce a voltage of around 200 volts with a power density of about 5 watts per square meter. If you think of the diagram before, many of the electronics that we have shown in that will be manageable using this sort of a power output, given that this power output can be obtained continuously. Here's another demonstration about from a recent video regarding our work. I'll play that for you now.
We've seen wind, tidal and solar power take off. But what about people power? A team at the University of Surrey is developing the technology that can store the energy that's released as we move. It means in future we could wear clothing that can charge our smartphones or watches. Alistair Fee reports.
Each of these players releases enough energy during one game to power a typical household for 10 minutes. But how do you harness that? A team at the University of Surrey is doing just that. In these research labs, they found a way to store the energy released through movement.
Movement between two materials, or someone jumping up and falling down, means that you have two surfaces that can come into contact. And in coming into contact, if you use the right type of energy harvesting materials, you can get contact electrification or induction of charge. And what we do is harness that energy, harness that power.
The heel of this shoe is one of the prototypes being looked at. It's designed to convert each step into electricity.
We are working on two different technologies. First one is how to use this current to directly drive different applications. Second one, how we can use this current to store in a battery or a capacitor and then later use this energy for useful purposes.
This technology is based upon one of the simplest experiments that children are taught at school. If you've ever rubbed a balloon on your jumper and then using static placed it on a wall, that is what underpins this research.
It's like the negative end of your battery, and your jumper is now the positive end of your battery. Soon as you put a device between the surface of the balloon and the surface of your jumper, you'll have current flowing, and that current allows you to drive this.
There's already huge interest from business. The team has been granted £1 million to develop the technology further and is working with retail, automotive and defence companies. What's being called people power could be the greenest and most sustainable form of energy ever. Alistair Fee, BBC South Today.
Okay, so that was a small demonstration of some of the activities that we were involved in while I was doing my PhD work at Surrey, and also at Loughborough University. With my current activities, we are developing this technology much further and then making better devices to tackle the problems related to the energy supply to portable and flexible electronic devices. And then as the next part of our study, what I have done is to address one of the key issues of this technology. As I have mentioned to you before, one of the main drawbacks of this technology is that the outputs can be very discontinuous. As you have seen in the previous demonstration, when you are operating a triboelectric device, the outputs which are generated are in the form of pulses. So when you're connecting it, you will be having a current pulse on the positive direction, and when you're separating, you will be having a current pulse in the negative direction. So in certain cases, this can be disadvantageous. For example, I'll show you the output patterns of a conventional triboelectric device, as you can see on the left hand side video here. I believe you can see this demonstration where when you're operating the device, there will be instantaneous lighting up of LEDs. That's because of the inherent nature of power generation of the triboelectric device. The alternative in this scenario, if you want to continuously power this device, would obviously be to capture this energy, store in a battery or a capacitor, and then use this energy in a later stage for useful purposes. And this is the development that we have done in one of the recent years, where using the original motion itself, we can generate triboelectric devices with a continuous power output. This technology is currently being patented, and it's an innovative technology that I have developed using a phase shifting technology of different triboelectric devices. And beyond human motion, other than wearable stuff and skin related triboelectric stuff, we can use any other energy source in our surrounding. For example, wind energy, the motion of vehicles, the vibration of machines, the energy from raindrops, ocean waves, any energy form which is in our surrounding and which can be obtained easily can be used for these applications to power a triboelectric device. And these kind of things not only for wearable devices but can also be used for different other applications. For example, for security applications, if we need to contribute to the energy needs of lighting street lights or something like that. So the applications are quite flexible and diverse for this technology. In terms of the project so far, there have been many contributors or collaborators to this project. So other than the Loughborough University that I'm currently working at the moment, and University of Surrey, my previous university, there are other universities like Exeter University, EMSC University in France, University of Moratour, and DZB Technologies, who are assisting us or collaborating with us in this project. So if any of you are interested in this energy technology, do get in touch in terms of if you need any information about this, and if you need to learn more about this technology, please do contact me. I'll help you as much as I can in this regard. And if you are willing to work on this technology also, there's a current project going on with University of Moratour in this research area. You can get more information about that as well. I'll go towards a few questions. How about efficient energy housing that can be used in a device? So Imad is asking a question about the use of energy harvesting methods that can be used in a device which track items. Yes, basically the device is to be really small and light so that it can be placed or pinned on a wallet, for an example, assuming for wireless connectivity, low energy. Yeah, so that sort of a application would be really useful, but the challenge in this scenario is what sort of energy source would be useful for this purpose. For example, if you are using a wallet and if you lost your wallet, you're about to find it using this tracker. I assume that would be the purpose. The challenge here is the energy harvesting device, if you're using it in real time, should be able to access the energy source. For example, if you lost your wallet in a corner of a room, there's no sunlight falling into that case, right? So in that case, and also if you lost your wallet in somewhere, there would be no movement available for this tracking device. So because of that, the energy harvesting devices may not be able to capture energy in real time at that point and then power the tracking device. The alternative for these would be to use an energy storage system in combination with the energy harvesting unit. For example, if you're carrying your wallet and during the time that you're walking along with this wallet, it will be able to capture some of the movement applied during our walking, and then it will be able to store that energy in a small storage unit, energy storage unit, And then once you need to activate the sensor or the tracking device, there might be a possibility that the stored energy can be used for this purpose. So there would be challenges in this regard, because the application that we're talking about in here is somewhat challenging in terms of obtaining power in real time. Uh, okay, Jayan is asking a question about whether TENGs will be able to power a temperature sensor powerful enough to detect the temperature levels of fever. Or would there be any sensors to detect any symptoms of the virus? Thank you. Okay, now with regards to this COVID virus itself, I'm not sure whether there are any devices available with triboelectric technology, but since powering a temperature sensor should not be very challenging. As I have shown in one of my previous slides, there are very efficient sensors with very low power consumption. So if we have a triboelectric device that will be able to capture a sufficient amount of motion energy and then probably to power a sensor like a temperature sensor, again we have to think about several aspects in this regard. Where are we going to place the triboelectric device? What sort of movements are there for the triboelectric device to capture energy, and what sort of energy management system would be required in this scenario? Because I would assume a thermometer kind of application would not be ideal for this, because we don't have much of a movement when we measure the temperature from the thermometer. But if we have something integrated to our bodies which can measure temperature, that would be ideal to be combined with a t-shirt or a pant or an application like that. Again, the capabilities are diverse. You have to select the right application and right device design and right energy management system in some cases to get the maximum benefit of these things. And then I would like to give you a brief introduction about the experiences that I had during my PhD studies and finding a scholarship to do the PhD studies. Obviously, if you are hoping to do higher studies in a PhD or a related degree, we would all like to have a scholarship, and the competition for these scholarships at the moment, especially in the UK. I have been in the UK, so I know the context of the UK, but I'm not very familiar with the other countries. If you think of Europe or the UK, the opportunities are becoming more and more challenging. So when you're trying to apply for a PhD position or to get a scholarship related to the PhD position, there are different aspects that you have to consider. Normally what happens is, when an advertisement comes on or when you contact a supervisor in a university, you will need to create a project proposal, and then you will be selected in a competitive basis among many applications. You will be shortlisted and you'll have interviews, and then you will be able to obtain the scholarships. So in terms of obtaining one, there are different things that you have to consider. First one, you might have to write a research proposal, which is a very, very strong aspect of your application. So you have to be very careful about the content that you put in, your research concept, how novel it is, how timely it is to the context, what are the research methods you are using. So basically you have to read a lot of state-of-the-art research, investigate facts, and then probably get support from different experts in the area to develop the research proposal. And then the universities also look strongly into how this research idea or research concept matches with the research or university university research strategy or group research strategy that you're applying for. There are different universities in the UK or in any country specialized in different areas. So if you are willing to apply for something that is relevant to you, make sure you go for the right university and right research group. And the extent that this research matches the university matters a lot when getting a opportunity for higher studies. And then you have to consider how impactful your research is. If somebody has done it maybe 30-40 years ago, that may not be as important to people as it would be for a new research idea. And the impact of research is highly valued in terms of what changes it would do to the society or to our understanding. And then the supervisors or mentors that you select for these studies is also very, very important. You have to go for a research group or a supervisor who has the expertise in your area and who has the quality of outputs in terms of producing good results and so on. And also, if you have collaborators or companies supporting your research ideas, that's an additional benefit. So in terms of the applicants, you yourself have to be prepared for such an application. You have to build up your profile by doing different things. In the UK context, a higher class in your basic degree would be very valuable. Ideally, a first class. That's one of the main selection criteria in some of the universities that I know. But if you don't have a first class, that's not the end of the world. You can still get opportunities using a second upper class degree or maybe a master's degree. So that's not a big issue. But if you have a first class, that's a very good starting point. And another thing that people are concerned at the moment in selecting applicants is the research experience that you have. Currently, having research papers is a big positive point. Mainly the journal publications are valued a lot, and also even the conference publications are also highly valued. Now the context is many of the other universities, for example, if you think of Chinese universities or Indian universities, they encourage their bachelor students to get involved in research. So their degrees might be 4 or 5 years, and then within that period they are involved in a large term or longer term research project, or they are part of a big project and contributing towards that project. As a result, in many cases they already have journal papers and other publications by the time they apply for a scholarship. So when you're comparing two different students with publications and without publications, the one with the publications obviously have a upper hand in getting selected. For the moment, I would say it's not an essential requirement, but if you can get a couple of papers published within your undergraduate research or other research activities, I would consider that to be a very positive point. And also, they would look for your awards and honors and other achievements that you have within your profile. And if you have some research experience related to the topic that you have suggested, that is also a positive point. In terms of getting through the interviews, it's also something very tricky, especially for Sri Lankan students in certain cases. Here they look how you face the interview in terms of your confidence, how well you answer the project, and how confident you are with your own research activities and in answering the questions. They don't expect you to have a very deep knowledge in the things that you're talking about. You have to know what you are saying, and you have to know it to the extent of a bachelor student, but they don't expect you to know everything. So you have to be confident in facing the interviews. You have to be confident about the answers that you're giving, and you should never underestimate the work that you have done, and you have to value your own work. So that's considered as a positive point when it comes to the interviews. Again, the language capabilities are a huge obstacle for some students in the universities in Sri Lanka. That's something you have to develop. That's very important thing that you have to develop. In any stage of higher education, you would need English to speak about your research, to write papers, to go for publications or whatever you do. So from the early stage itself, try to develop your language, both spoken English and also writing different articles and stuff. You can practice them and make sure you are in a good position when you finish your bachelor's degree. That's also a very, very important aspect. Also, you might have to know your targets, what you want to do after this many years, and what sort of field you want to study in. Many of the people, as a bachelor students, even I was a bit unsure about moving into a new country and start working without knowing anyone in the surrounding environment. But it's nothing to be scared of, especially in the PhD. They don't expect you to do what you did in your bachelor's. It's most likely that you will be working in an entirely new and entirely different research field. That's expected from you, from a bachelor student. That is expected. So you don't have to be scared of selecting a new field or starting to do something that is new to you. That's part of the process. So you will learn in the job, and you will start doing these research activities as the time passes on. For example, from my own experience, I did a field related to textiles and materials engineering when I was doing my bachelor's at Morato University. But at Surrey, I was mostly involved in electronics engineering, nanotechnology, and Maxwell's electromagnetic equations. So those are entirely different research areas. But when you start your degree and when you slowly learn these basic things, you will be able to manage these things fairly better. And from my experience, the students who are coming from Sri Lanka are able to perform really well in PhD studies, probably due to our education system and the toughness of the systems that we have passed through from the O levels, A levels, and university. It is quite manageable when you come here, and then you can perform really well from the examples that I have known. And you have to be persistent in the PhD project. There will be a lot of drawbacks, a lot of discouraging outputs, and so on. But you have to be open-minded, learn new things from juniors or from seniors, from supervisors, and always try to develop yourself for your own betterment. And that's the trick, as far as I'm concerned, in being successful for your PhD project. Okay, Imad has asked another question regarding my previous question. Is it possible to use piezo mechanical human motion energy harvesting? Else, if energy harvesting is challenging, how about possible energy saving methods? Okay, so again, even in the case of a piezoelectric generator, you would need the movement for the piezoelectric device to capture the energy. Triboelectrics is also the same. Those two are very similar technologies where you capture the motion or a vibration of an energy source and then convert it into electrical current. Even in the piezoelectric case, you need some sort of mechanical motion in order for you to convert it into electricity. So all the restrictions that I have mentioned before for triboelectric devices might exist for piezoelectric devices as well. But again, as I have mentioned earlier, you can always capture the energy when it is available. For example, when you're having the wallet on your pocket or something, you can capture energy, and at a later stage, you can use that energy for your application purposes. All right, so that's my presentation for today, and I hope I was able to give you a brief idea about the technological developments in the current context. I know some of you might find it difficult to understand without a further explanation in certain aspects, but if you had a brief idea about the available technologies and how we can use these technologies to do different things, that would have been my idea or objective in doing this session. if you have any questions, or if you are interested in knowing more about this technology, just drop me an email on r.i.dharmasena@loughborough.ac.uk, r.i.dharmasena@lboro.ac.uk, and I will be able to help you as the best I can. Thank you very much for joining me for this session, and I also thank the SCF Foundation and Asel and the crew for inviting me for this session. Thank you very much.